Hi, I'm Ben-Yaakov. This presentation is entitled Wien Bridge Oscillator Stabilization by Incandescent Lamp and more. Now, the Barkhausen Stability Criterion teaches us that oscillations will be sustained if the loop gain is 1. That is, if the gain of, say, this part here, say it's an amplifier and a feedback part, if the product here is 1 for the amplitude, absolute value, and if the phase coming back will be 0. Now this is intuitively clear because if you have a signal that goes all the way around and then it comes back with the same amplitude and phase, then you sort of sustain the oscillation. So if the loop gain will be 1, then you have oscillation. If it is larger than 1, then the amplitude will start rising or go up and up. And if the loop gain is smaller than 1, then you have a decay of the oscillation and it will die. Now in this presentation, I'm going to concentrate on the Wien bridge oscillator. Now this is the Wien bridge itself. We have here, one arm here has 2 impedances, and then there is a voltage divider, so it's a bridge here. And it can be shown that if R1 is equal to R2, these resistances and these capacitances are equal. And for a frequency which is 1 over 2 pi RC, then the divider here will be 1/3. That is, the voltage here is 1/3 of this voltage here coming in. And so therefore, if you have a voltage divider here, resistive voltage divider, 1/3, then the bridge will be balanced. And then this signal goes into an amplified and going back here. So this is the idea of the Wien bridge oscillator. Now, since the attenuation here is 1/3, then R4 has to be half the value of R3. Okay, so this is the relationship that will balance the bridge. Now, when drawn like this, it's not clear what is the relationship to the Barkhausen Criterion. And here I've redrawn the same circuit, except that I've taken this resistor which was here and put it here. Now it becomes clear that we have here a non-inverting amplifier, okay, from here to here. And then we have a divider here, an impedance divider. So we have the 2 parts. We have an amplifier, and this is the gain of this amplifier. And then we have this divider, and this is the attenuation of this divider. And the product is this times this. Now for the condition that I've stated, this is 3 and this is 1/3. So therefore the loop gain is 1, exactly as the Barkhausen Stability Criterion teaches. However, the Barkhausen Stability Criterion doesn't tell us anything about the amplitude. Now theoretically, if you start with a given amplitude, it should be going all the way around and the same amplitude will stay, but this is of course impossible in the real world, in the physical circuit. So there must be some arrangement to stabilize the amplitude. But not only that, for the oscillation to keep going, this relationship, the balancing of the bridge, has to be kept all the time. This is impossible from the physical point of view. Now there are changes in the values of the resistors, temperature changes, etc. So there must be some mechanism that will balance the bridge such that the oscillation will not decay or run away. Now this can be done by making one of the resistors, say either R4 or R3, variable, such that the system can adjust it so that the bridge will be balanced all the time. And this is the issue of stabilizing this oscillator. Now, as far as I can tell, the first paper that actually tackled this problem was this paper by Ben-Yaakov, the bridge stabilized oscillator. This was published in 1938. This is actually 1 year before I was born. So this is from this time, like 87 years ago. It's amazing. So he considered this problem, and here is the circuit that he was suggesting. And this is for stabilizing the oscillation around the crystal that is used as a resonant circuit. Now this is the expression for the series resonant of this crystal. It has a real part and an imaginary part. And at resonance, this imaginary part becomes zero. So here we have this oscillator, which has this amplifier here. We have a bridge, and here is the input to the bridge. This is the input to the bridge. This is the output of the bridge. And as you can see, we have here now a divider which has a variable resistor, and the variable resistor is realized by the filament of an incandescent lamp. Now the resistance of the lamp increases with the power or current. So it starts in this case from 40 ohm, then all the way to about 200 ohm. And this is used in order to tune very finely the bridge. So we have a bridge here. At the operating point, we have to have a voltage here which is approaching zero. And this is done by adjusting this resistance to this resistance, which is accomplished by the fact that the current now is flowing through this filament, heating it up, increasing the resistance until, of course, we get to a voltage here which is about zero, and then we have a stable operation. So what we have here is at the beginning the voltage at the output is low, and then the resistance is small resistance meaning high voltage here. So the amplitude of the oscillation increases, the input here becomes smaller and smaller until it reaches about zero, and this will be the stable operation. So this was the idea, and it is used up to date for stabilizing the Wien bridge oscillator. Now, as far as I know, the first company who started to use this concept was HP, and they have implemented it in a signal generator that was produced by the old days by HP. Now here is the realization by Mechem. What we see here is a thermionic bulb, a vacuum tube. At that time, of course, there were no transistors, let alone MOSFETs. And this is the amplifier. There are some transformers to isolate parts of the circuit. The two grounds are not the same. And this is actually an implementation of the circuit diagram that I've shown earlier. And here is the implementation. These boxes are the capacitor. I guess we see here the resistor. I guess this is a trimmer to adjust the resistances. And I think that we can see the lamp here behind it. This is the vacuum tube, and I guess this is the transformer. Now the results were really amazing. The circuit provides constant output amplitude, and then purity of waveform, that is lower harmonics, and then the stability of the frequency around this crystal oscillator was 2 parts in 10 to the 8, which is very, very good. Now this same idea is now used today, and has been used for quite a while, in the Wien bridge oscillator. Here R4 is replaced by an incandescent lamp, or by a lamp plus a resistor. It could also be realized this way. And the idea is again that at the beginning there's low voltage, low amplitude, but the gain is larger than 1. And here is the input, positive input, so there's positive feedback. So current starts to flow here, and the resistance of this lamp now goes up, and therefore the voltage here becomes lower and lower. This is 1/3 of this voltage, and this now, as the resistance goes up, this voltage increases, and therefore the difference becomes smaller until it hits around zero, and this will be the stable. There is, however, a hidden parameter that usually it's not talked about that much, but it is very important to realize that the thermal capacitance of the filament is very important in the operation of the circuit. Now, if we have a filament, it has some mass, and as we pump in power, the temperature goes up. Some of the power is conducted outside, and some is radiated as visible and infrared. And the equivalent circuit, the thermal equivalent circuit of this situation is we have a current source which represents the power coming into the filament. We have the thermal capacitance which stores the thermal energy, and then we have the thermal resistance to the ambient. And here I'm showing actually some radiation of the visible and infrared light that will be a small part of the total power. And this will be especially at high temperature, of course. At low temperature, this part is very small. Now, why is this important? Because without this thermal capacitance, we'll be moving on the curve of the VI curve or the resistance back and forth, and this will introduce distortion. Now, if we have this capacitance, then the high frequency is not sufficient to change the temperature that much or very little. And consequently, what we see is like this slope here, a constant resistance, and therefore the harmonic content will be very small, and therefore we can get a very pure sinusoidal waveform. This is very important. And here is a design example. This is actually by DigiKey, the tech form that they have. And here we have an amplifier. This is now the impedance divider, and this is the resistive divider. And here we have the lamp, and the resistance has to be half of this one, so this is 300, and therefore the operating point, this should be 150 ohm. This is the power supply of plus minus 12 volt. And here we have information about the resistance of this tiny lamp that is used. This is voltage, this is DC voltage fed to the lamp, and we see that the resistance goes up from about 100 to about 700 ohms, and the steady state point should be around here, 150 ohm, which correspond to 10 milliamp or 100 or 1.5 volt across the filament. Now, if the voltage here is 1.5 volt, which is like the RMS, then the peak value expected is the square root of 2 times this DC value, which is 1.5, and then the voltage across the divider, that is the voltage here, will be 3 times larger, times square root of 2, we get 6.36 volt. Now the amplifier has to be capable of delivering this 10 milliamp at least, a little bit more of course for the other part of the circuit. And we see that at 10 milliamp we have some drop here, so even if the total current will be higher, I guess this is 25 degree, it's okay if the amplitude that we need is like 6 volt here. And indeed, this is the plot given in the write-up. We see that the amplitude, the peak is 6 volt. Well, this may not be exactly 1.5, maybe it's 1.4. So it's really consistent with what I've expected. So let's do some simulation to get a feeling of what is really happening. So here is the bridge, and I've replaced this resistor, this one, by a variable resistor, which depends on the voltage at this point. Now this voltage now is generated as a function of the absolute value of the current. So it is a function of the current, and therefore the resistance is a function of the current. This is assumed to be exponential. And here I have this capacitor, and this is very important, as I've said, to mimic this thermal capacitance. So this is just arbitrary value. This is just for demonstration, of course. And here is what is really happening. We have the startup here. This is the output voltage. This is the input to the amplifier. At the very beginning, it's really very high, but then it gets to very small values. And this is the voltage generated on the capacitor. And you see it's pretty smooth and very little ripple on it. Startup transient, we see a pretty stable operation. There is an issue of a startup, and that is at the very beginning, if the output of the amplifier is 0, the input is 0, so it is supposed to stay at 0 voltage. In the real world, there is always noise and offsets, and therefore oscillators tend to start without any problem. In simulation, it might get stuck. In this case, I'm showing here what is really happening by zooming in. This is the output voltage, it's 0 at the beginning. This is the input to the amplifier, and this is the zoomed input voltage here at the amplifier. It's 120 microvolt. You see that for some reason, due perhaps to the final numerical resolution, or maybe there is some offset to the amplifier or leakage current that they've put in. Anyhow, it starts to diverge. Once you have a output here, due to the positive feedback, then you get the start up and the current starts to grow up, as we see here on the capacitor. Now the output waveform is really very, very clean. I'm showing here the voltage on the capacitor. You see it's very, very stable. It's millivolts of changes around the 1.6 volt. And I'm showing actually the resistance of the filament. And this is by dividing the voltage by the current. Each one is sinusoidal, but due to the fact that we are stabilizing the filament resistance at about a constant value, then the resistance is constant, even though the amplitude is fairly large. And you see that it is around, in this particular case, 5 kilo ohm, as it should be, because we have here 10 kilo ohm, and as we know, this has to be half of this, so it really stabilizes at 5 kilo ohm. Now this is the FFT of the signal at the output. It's very good. So it's about, this is like 10 dB, and this is minus 65, so it's about minus 75 dB for the third harmonic, which of course is very, very nice. Another way to stabilize the amplitude is by clamping. And what I'm showing here is a network that has, first of all, a 11 kilo ohm, which is larger than is required, and therefore the loop gain will be higher than 1. But then in parallel, I have this network here with diodes, such that when the voltage here is above the voltage drop of the diode, then it starts conducting, and then we get an equivalent resistance which is lower than 11, and at the steady state it should be, of course, 10. Okay, this works very nice. One has to be a little bit careful in choosing the components here, not to distort the waveform. And here is an example. We see here, this is the output voltage, this is the error voltage, very nice, also sinusoidal. And here is the spectrum, the FFT. It seems to have a higher third harmonic, but again, it's really very, very good. We have here 10 dB again, and this is like minus 45 degree, so it's minus 55 dB, which is very nice. Now, there has been many other suggestions of how to stabilize the oscillator and to keep the amplitude. Now, amplitude stabilization is an important issue, and you need an extra effort in order to make sure that the amplitude will stay constant as you wish. The example that I've shown earlier will not produce a very stable amplitude. It will change with temperature. It'll be about constant, but it's not really very constant. Now here is an example given by analog devices of a circuit, rather an elaborate circuit, but the concept is important, so this is why I brought it in. So we have here the Wien bridge itself. Now the variable element is a JFET. By changing the voltage at the gate, you can change the resistance. Now here, there is already 4.5 kilo ohm resistance. So this is 10 kilo ohm. So we need an extra 470 here. We have here already 750 ohm. So we need this JFET to have a resistance of 1258, 1.2 kilo ohm. I've neglected this part here. Now, the important part is the following. The amplitude is measured by a device, by an element that actually is measuring or calculating or sensing the RMS. It's producing a DC which is proportional to the RMS of the value seen here. So this value now, the DC representing the RMS, is first of all amplified, but then compared to the reference that you wish. This part is very important to keep the amplitude. Because if you measure the amplitude one way or the other, either the peak or the average or the RMS, whichever is important for you, and then compare it to a reference, and then you have an integrator here. Now this capacitor or this integrator is actually mimicking this thermal capacitance of behavior that I've mentioned, and then feeding into the variable element, then you can control the amplitude very, very precisely. And they are saying that this is very, very stable. And of course, it has also very low harmonics. Okay? So, although this is a complex circuit, the concept of measuring the amplitude and then comparing it to a reference plus this smoothing is a concept that can be used to stabilize the amplitude very accurate. And here I'm showing part of the datasheet of the JFET, and you see that the resistance at 0 volt is between 2.5 kilo ohm to 1.7, and we do need 1.2. So by small changes of voltage around 0, you can actually get the value that is needed. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it of interest, and perhaps it'll be useful to you in the future. Thank you very much.